Hello there.
Welcome back to part 2 of our Ascend to Celestia developer guide. With our environment, collision triggers, and data structures fully set up in part 1, it is time to build the actual brain of our game mode. In this section, we are focusing entirely on the progression master graph, which we call GetFloorStats. This single node graph acts as the central node graph for the entire game. Every time the player walks through a series of triggers to ascend the tower, this graph fires up in the background to dictate exactly what should happen next. Because this system is so large, we are going to break it down into clean, manageable composite node graphs. Together, we will build a dynamic enemy scaling engine that perfectly balances exponential math curves against the player's current team level. We will also create a boss heat system that organically paces your major encounters and prevents bad RNG. We will also do a background health monitor that checks the team's vitals to offer emergency regen buffs. Finally, the dynamic tower spawning system that generates the infinite climb and manages our game's memory. By the end of this video, your tower will be fully functional, infinitely scalable, and highly optimized.
Nice.
Next is the progression master graph, GetFloorStats. Whenever the player transitions between areas and the calculate enemy level signal is fired, this graph steps in to orchestrate everything. It determines if the player has beaten the game, checks if they need a boss fight or a heal, and executes the dynamic difficulty math we built inside our composite nodes. Here is the breakdown of how this graph flows. 1. Milestone and victory check. Floor 31 check. The system checks if the player reached floor 31. Zone complete. If Boolean returns true, it fires the settle stage signal to end the run and distribute rewards. 2. Executing floor mechanics. If the run continues, it simultaneously triggers 3 parallel updates. Floor advancement increments the player's current floor counter by 1. Boss heat system updates the heat calculation. If heat hits 100, it fires a boss event to spawn a boss. Medic scanner checks team health. If health is critically low or a character is KO'd, it fires an HP threshold signal to open the buff selector. 3. The scaling calculation chain. The math engine calculates the next room's difficulty via a 4-step chain. Get average char level sums up the total power of the player's party. Set base level calculates the true average, applies the difficulty modifier, and caps the minimum level at 30. Calculate growth rate calculates an exponential multiplier so enemies hit their max level cap exactly on the final floor. Set enemy scaling combines exponential and polynomial curves to output a balanced, rounded enemy level. 4. The final output, spawn information. Once the math finishes, the graph fires the spawn information signal. Next wave, it sends the updated current floor and the new enemy level directly to the spawning system to start the next battle. Next, let's take a look at the composite node graph, get average char level.
No, God! No, God, please, no! No! No!
Oh no! Anyway, look.
Its primary job is the crucial first step, looping through all characters in the player's party and adding up their levels to calculate a team total. The graph uses a list iteration loop to cycle through every character in the team list one by one. Get character attribute. For the current character in the loop, it grabs their specific level. Split structure. It looks at the current total underscore team level already saved in the player's stats. Addition. It adds the current character's level to that ongoing total. Modify structure. It immediately saves this updated sum back into the total underscore team level variable. Once the loop finishes checking every single character on the team, it fires the loop complete execution pin. Moving on, let's look at the composite node graph, set base level. This composite node graph picks up right where the last one left off. Its main job is to finish calculating the player's true average team level, apply a difficulty modifier, and establish a base enemy level, with a built-in safety floor so enemies don't get too weak. 1. Calculating the true average level. Remember how the previous graph added up all the character levels? This graph finishes the math. The division, it takes the total underscore team level and divides it by the total number of characters, get list length. Saving the result, it saves this final number into the AVG underscore team level variable inside the player's stats. 2. Fetching difficulty settings. Down in the bottom left corner, the graph looks up the game's current settings. It reads the player's choice from a selected difficulty variable. It extracts a specific balancing modifier called -_init enemy LVL, initial enemy level subtraction. 3. The math and the safety check. Next, the graph calculates what the baseline enemy level should be and makes sure it isn't too low. The subtraction, it takes the team's AVG_team level and subtracts the difficulty modifier, -_init enemy LVL. The check, it checks if this new calculated number is less than or equal to 30. 4. Setting the final base level. Using a double branch, the graph routes the logic to save the final base level into the area's floor variables. If yes, value is 30 or lower, the graph clamps the difficulty. It forces var_base enemy level to a baseline of 30 so early game or low level areas remain a standard minimum challenge. If no, value is higher than 30, the system scales dynamically. It sets var_base enemy level to the exact result of the subtraction calculation, allowing enemies to scale up nicely with high-level players. Then, we have the composite node graph calculate growth rate. The graph calculates the constant growth rate using the following equation. The base, max_enemy limit, var_base enemy level. This calculates the total scaling ratio required for the entire game. It figures out how many times stronger an enemy must become from the absolute beginning of a run to the absolute maximum endgame cap. The exponent, 1, max_floor limit plus 5, this fraction divides that total scaling requirement evenly across all progression steps, floors. The plus 5 acts as a safety buffer so the progression curve doesn't spike too aggressively or crash the engine if the floor limit was accidentally set to 0. This formula is a standard implementation of a geometric growth rate, essentially the compound interest formula used in finance, but repurposed for video game scaling. Here is why this approach is highly effective for roguelikes, dungeon crawlers, or arcade games. If you used a flat addition method, e.g., adding +2 levels per floor, early floors would feel massively difficult, while late floors would feel incredibly easy because player power naturally grows exponentially. This exponential root structure ensures that the enemies scale proportionately to their current strength rather than linearly. The biggest benefit of this formula is that it works entirely backwards from your game's maximum constraints. No matter how low a player's starting level is, or how long the game run is, max_floor limit. This math calculates the exact percentage multiplier needed to ensure enemies smoothly reach the maximum level limit right as they approach the final floor. By adding 5 to the max_floor limit before performing the division, it prevents division by 0. If a designer accidentally creates a dungeon with a max_floor limit of 0, the engine won't crash trying to divide by 0. It also flattens the curve. It slightly extends the denominator, meaning enemies won't hit an absolute mathematical ceiling too quickly, allowing the gameplay curve to feel challenging yet fair as players reach the final stages. Other than that, we also have the set enemy scaling composite node graph. This composite node graph takes all the data we gathered earlier, the floor variables, and our custom growth rate, and calculates the exact integer level for the enemies spawning on the current floor. To do this efficiently, the graph splits the logic into 2 parallel calculation tracks before merging them into a final safe value. This is a highly sophisticated hybrid scaling curve. Instead of relying purely on one mathematical model, it blends exponential growth with a polynomial correction term to create an idealized gameplay progression arc.
Huh?
Here is why this specific breakdown works for game balance. This is the exponential core formula. This is your baseline scaling. On floor 1, current floor 1 equals 0. Any number to the power of 0 is 1. Meaning enemies start exactly at your calculated var_base enemy level. As the player ascends the floors, the level multiplies smoothly. It establishes a predictable, natural sense of progression where things gradually feel tighter and more dangerous with every new floor. Here is the acceleration or catch-up term formula. This solves a common problem in dungeon crawlers where pure exponential scaling can occasionally flatten out or fall short of the final boss's intended difficulty if the player's entry level was unusual. By subtracting the base level from the max limit, the game isolates the exact level deficit needed to reach the ceiling. Dividing it by the total floors squared, max_floor limit squared, and multiplying it by the floor progress raised to the growth rate creates a late-stage acceleration curve. In early floors, this term adds almost nothing. On the final floors, it accelerates drastically to ensure enemies aggressively scale up to meet the climax. Next we have the safety capping mechanism. Here we are combining two aggressive scaling methods. The math could overshoot our intended balancing. The take smaller value node compares our combined total against the absolute max _ enemy limit and picks whichever number is lower. Then it saves this perfect, clamped whole number into the enemy level variable, which is passed directly to the game's spawning system. Now let's take a look at the composite node graph, the boss heat system. This composite node graph manages a dynamic heat system to determine when a boss encounter should trigger. Instead of spawning bosses completely at random or on hard-coded floors, the game uses an accumulation mechanic. The longer the player survives without facing a boss, the higher the heat rises. Once heat hits 100, a boss fight triggers, and the system resets. Here is how the graph processes this logic step by step. Before any heavy math happens, the graph reads the player's selected difficulty settings to check if they are still in the introductory floors of the zone. First, the condition. It checks if the current floor is less than or equal to the level ramp-up threshold. Second, the grace state. If yes, the game forces the heat level to stay locked at a low, safe baseline value. This guarantees players won't be ambushed by a boss right at the start of their run. Once the player surpasses the ramp-up floors, the double branch switches over to calculate dynamic exponential heat accumulation using this formula. These are some of the variables in detail: added heat and heat multiplier, balancing values tailored to the player's chosen difficulty. Const _ growth rate is the custom scaling factor we calculated earlier. The exponent, current floor 1, level ramp-up, ensures that the deeper the player goes past their safe floors, the faster the heat accelerates. Adding the existing heat level heat multiplier creates a compounding effect, ensuring the thermometer keeps marching upward. After updating the calculation, the graph routes the new total to a safety evaluation node, which is the threshold. It checks if the newly calculated heat level is greater than or equal to 100. A final double branch updates the game state depending on whether the heat limit was breached. If heat greater than equals 100, boss floor event, it sets the boss floor variable to true, passing a yes data signal to the spawning engine. It also triggers the boss event signal to tell the enemy spawner to spawn a boss. After that, for the crucial step, it uses a modify structure node to overwrite the heat level and reset it cleanly back to 0 so the loop can start over for the next section of the dungeon. If heat less than equals 100, normal floor, it sets the boss floor variable to false. Then it saves the newly accumulated calculation value back into heat level structure so it can carry over into the next floor. We also have the Regen Event composite node. This node acts as a medic scanner for the player's party. It calculates the team's overall health percentage and checks if anyone has been knocked out. It then outputs simple true, false signals that the game's buff selector can use to offer life-saving choices to the buff selector once a fight has been completed. Here is how the logic flows. Before doing any math, the graph resets the team's stored health data. It sets the current _team HP and total _team HP to 0, and resets the char down, character down, flag to false. This ensures we are starting with a clean slate for the current floor. The graph grabs the list of all characters in the player's party and runs them through a list iteration loop. First, checking for casualties, it checks each character's current HP. If it equals 0, it triggers a modify structure node to flip the char down flag to true. This tells the game they need a revive. Second, accumulating HP, it takes the character's current HP and adds it to a running total for the whole team. It does the exact same thing for the character's max HP. Once the loop finishes checking every character, loop complete, the graph figures out how bad of a beating the team has taken overall. First we have the division. It divides the combined current _team HP by the combined total _team HP. This gives us the team's current health as a percentage, for example, 0.5 for 50% health. Then we have the threshold check. It uses a less than or equal to node to check if that percentage has fallen below your specific danger threshold. Finally, the graph saves these results and fires them out of the node's output pins. Below HP threshold, Boolean, outputs true if the team's total health percentage is critically low. Character down, Boolean, outputs true if at least one character in the party has 0 HP. Congratulations! By linking all of these custom composite nodes together into the GetFloorStats master graph, you have just built a highly intelligent, fully dynamic progression engine. Instead of relying on hard-coded levels or pure, chaotic randomness, your game can now think for itself. To recap what this single graph accomplishes every time a player moves to a new floor: dynamic enemy scaling. It uses a hybrid math curve to ensure enemies are perfectly balanced against the player's level, accelerating smoothly toward a climactic final boss. Smart boss pacing. It uses a heat system to guarantee boss encounters feel organic and well-paced, protecting players from bad RNG. Adaptive safety nets. It constantly monitors the team's health, ready to offer crucial heals or revives if the player is on the brink of a game over. Automatic progression. It seamlessly tracks floor numbers and automatically triggers victory conditions when the final stage is reached. Now that this massive mathematical brain is completely wired up, it needs a host. To make this logic live in your game, take this completed GetFloorStats node graph and attach it directly onto your player entity. Because it is attached to the player, it will constantly travel with them from room to room, passively listening for the calculate enemy level signal to do its magic.
Yeet!